Welcome to this second webinar, and the workshop this time is called A New Approach to the Teaching of Areas on Graphs and Trigonometric Identities. And it's all based on a simple rule which is contained in the Vedic Maths book in chapter 39 on analytical conics, called the product of the means minus the product of the extremes. And this is mentioned once in the book in connection with finding a product of the means minus the product of the extremes is 10 times 3 minus 4 times 8. And here the word means the middle two numbers, 10 and 3, and the extremes are the outer two numbers. So we take this difference of the product of the two, and that gives us the equation of the straight line 6x minus 5y equals minus 2. But this rule can also be used to find the area of a parallelogram where one of the corners is at the origin, and here we have the two adjacent corners at 6, 3 and 4, 5. And applying the rule product of the means minus product of extremes to these coordinates, we have 5 times 6 minus 4 times 3, which is 18, and that is the area of the parallelogram. If we place the coordinates around the other way, we still get, then we arrive at 4 times 3 minus 5 times 6, we get minus 18, and we just take the positive value of that. And let's have a look at some examples of this. So in the first example, top left, we can find the area as 7 times 8 minus 2 times 4, and that gives 64. And the next example on the right, we have a parallelogram here with a corner not on the origin. And the method here is to slide the parallelogram so that it does have a corner on the origin. Now, the bottom left-hand corner at 1, 2, so we're going to subtract 1 from each of the x coordinates of the other two corners and 2 from each of the y coordinates. So 5 is reduced by 1, giving 4, and 11 is reduced by 1, giving 10. And then the y coordinates, 8 and 4, are both reduced by 2. And then we apply the same rule, 6 times 10 minus 4 times 2 gives 52 as the area. Bottom left, we have a triangle. Well, every triangle is half a parallelogram. And so we can just use the same rule, 6 eighths minus 3 fours, which is 48 minus 12 is 36, and then half the answer to give 18. And with a triangle that doesn't have a corner in the origin, we can slide it down so that it does. So in this case, we need to subtract 2 from each of the x coordinates and 3 from each of the y coordinates, giving 2, 4, 6, 1. And then apply the rule, 4 sixes minus 1's 2 gives 22, and halve that to give 11 as the area. So how does this work? The most direct one is the transforming of a unit square using a matrix transformation. So in green here we have a unit square with the two corners adjacent to the origin at 1, 0 and 0, 1. And the parallelogram shown has corners at CD and AB. Applying the transformation matrix CDAB to the corners of the unit square results in the same matrix, because 1, 0, 0, 1 is the identity matrix. And it is the case that the determinant of a 2 by 2 transformation matrix gives the area scale factor. The determinant is b times c minus a times d, and the modulus, the positive value of that, is the area scale factor. But since the unit square has area of 1, then the parallelogram has that area. Takes a parallelogram with corners at CD and AB, and by moving parts around of this parallelogram, we can show that it is equal to the difference of two rectangles. So let's have a look at this. So the parallelogram has now been transformed into this shape, which can be seen to be the difference of two rectangles, a large rectangle minus the small one. And if we have a look at the distances, the lengths of these shapes, the large rectangle has area b times c, and the small rectangle has area a times d. And so the area is BC minus AD. This application of this rule is in a one-line proof of Pythagoras' theorem. So here we have a square which has been rotated with one corner remaining on the origin, and the side length of the square is c. And I've called the coordinates of that first corner AB, and it follows that the coordinates of the other corner are minus B and A. We can then apply the rule to these two pairs of coordinates to give the area of this square, because after all a square is a parallelogram. And so the area of the square is a squared minus b times minus b. But the area of the square is also c squared, and hence c squared equals a squared plus b squared. Now moving on to trigonometric identities, I'll first look at some of the basic ones, which can all be got from a single diagram. And here we have a circle with a point P somewhere on it, which makes angle, OP makes angle theta with the x-axis. And I've called the radius 1. Now it turns out that the distance OA is cos theta, because adjacent over hypotenuse is cos theta, and since the hypotenuse is 1, then the adjacent is just cos theta. Similarly, AP is sine theta. And using similar triangles, in which on this diagram there are in fact five triangles which are all similar, which are OAP, APB, OPB, OPC, and OCB. And from using these similar triangles, we can get the lengths shown as PB is tan theta, OC is cosec theta, PC is cot theta, and OB is sec theta. The very names of these trigonometric functions are linked. So tan theta is linked to cotan, and the prefix co is Latin for with. So what goes with tan theta to complete the triangle OBC is cotan theta. Similarly, what goes with sec theta to complete the triangle is cosec theta. And what goes with sine theta is the cosine of theta. Now, from the definition of tan theta in triangle OAP, it follows that tan theta is opposite over adjacent, which is sine theta over cos theta, and that gives the first identity. The next three are got from applying Pythagoras' theorem to the triangles. So in triangle OAP, we find that sine squared theta plus cos squared theta is 1 squared, which is just 1. In triangle OPB, we have that 1 plus tan squared theta is sec squared theta. And in triangle OPC, we have 1 plus cot squared theta is cosec squared theta. For triangle, and here we have a triangle with one corner at the origin, the next corner on the x-axis at B0, and it follows from the trigonometry that the third corner is at a cos theta, a sine theta. And we can apply the rule to find the area of this triangle. It must be half the area of the parallelogram, and so it is half b times a times sine theta, or ab sine theta, half ab sine theta. And we can also use this rule, product of the means minus the product of the extremes, to establish the sine. And here this looks a little bit complicated, but in fact it's just one triangle rotated into three positions. In the first diagram, we have the triangle with C at the origin, A on the x-axis and B up there. The coordinates of B are A cos C, A sin C. And from those coordinates, using the rule for area of triangle, we've got that the area is a half AB sine C. In the next diagram on the right, the triangle is rotated with corner A on the origin, and it follows from that that the area is a half BC sine of A. And in the bottom left, the triangle is rotated again with a corner B on the origin, and here the area is a half AC sine B. Now it's the same triangle, and so each of these three areas is equal, from which we have that AB sine C equals BC sine A equals AC sine B. And taking the first two, AB sine C equals BC sine A, and dividing by B, we end up with A sine C equals C sine A. And taking the second two and dividing through by C, we have that B sine A equals A sine B. And rearranging these, we arrive at the cosine rule. Then we can get the cosine rule. The cosine rule, in fact, is a special case of, or no, I should say a more general case of Pythagoras' theorem. So here we have a triangle, and with sides ABC, and the squares of those sides are drawn in blue. The square on the right with edge length C is going to be rotated and reduced in size to give the red dotted square, and similarly the bottom square is going to be reduced to give another red square, and then we can use Pythagoras' theorem on the result. So in that I've called this right angle triangle that's going to be formed with hypotenuse A and base B dash and height C dash. Pythagoras' theorem would then give that A squared is B dash squared plus C dash squared. Now C dash is C cos alpha, and B dash is B minus C sine alpha. And so we can write that A squared is B minus C sine alpha all squared plus C squared cos squared alpha. And multiplying out these brackets, we have B squared minus 2BC sine alpha plus C squared sine squared alpha plus C squared cos squared alpha. And those two last terms on the right simplify to C squared, because sine squared alpha plus cos squared alpha is 1. And that results in the cosine rule, A squared equals B squared plus C squared minus 2BC sine alpha. Now, sine alpha is the same as cos of angle A. And so we land up with A squared is B squared plus C squared minus 2BC cos A. Now let's have a look at compound angle formulae. Here the parallelogram has two adjacent corners, adjacent to the corner on the origin, I should say, at cos A sine A and cos B minus sine B. And the angle between those two sides of length 1 is A plus B. So applying the formula to the coordinates, we have that the area of this parallelogram is sine A cos B plus cos A sine B. And then also using the formula for the area of a triangle, a half AB sine C, and remembering that the parallelogram is double that, we have that the area of this parallelogram is 2 times a half times 1 times sine of A plus B. And that simplifies straight away to sine of A plus B is equal to sine A cos B plus cos A sine B. Sine of A minus B. And here the parallelogram has an angle of A minus B inside it. Applying the formula, we immediately arrive at sine of A minus B is equal to sine A cos B minus cos A sine B. Formulae for cosine. Here we have the angle B, the first side of the parallelogram is angle B with the x-axis, and the other side of the parallelogram is angle A with the y-axis. So the corners are cos B sine B and sine A cos A. And the angle in between is 90 degrees take away A plus B. Applying the formula, the area of the parallelogram is cos A cos B minus sine A sine B. And that's equal to, using the area of the triangle formula, doubled, sine of 90 take away A plus B. But 90 take away A plus B is, sine of 90 take away A plus B is the same as cos of A plus B. And hence cos of A plus B is cos A cos B minus sine A sine B. And this diagram gives us a way of finding the formula for cos of A minus B. So one of the corners of the parallelogram lies at cos B minus sine B, and the other corner as sine A cos A. And the angle inside the parallelogram is 90 degrees take away angle A and then add angle B. And so it is 90 minus A minus B. So the area is cos A cos B plus sine A sine B, and that's equal to the sine of 90 minus A minus B, which is the same as cos of A minus B. And hence we land up with the formula as shown. I haven't found a diagram for the compound angle formulae for tan, but this is usually done just by dividing the formula for sine by the formula for cosine. We'll now look at a method for finding the distance of a point from a line. And this is a fairly original approach and certainly a lot easier than the approach found in the Wikipedia site, which I'll show you later. We have here a point 4,4 and a line passing through the origin with equation y equals minus 2/3 x. Rearranging that equation, we can see that 2x plus 3y is 0. And the question is, what is the distance between the point and the line? I'll call it h. First of all, draw a line parallel to the given line through the point 4,4. We can then form up a parallelogram by drawing this line from the origin up to 4,4 and then choosing a point on the original line, a convenient point, and drawing another line parallel through that point. So I've chosen 3 minus 2. And where have I got those numbers from? I've got those numbers from the equation 2x plus 3y equals 0. By transposing the two coordinates and setting a minus sign, adjusting one of the coordinates to a minus, these two numbers satisfy the equation, and so that point does lie on the line. And those, it turns out, are the coordinates of the most convenient point to use. So we can look at the area of this parallelogram using our formula. And so the area of the parallelogram is 4 times 3 minus 4 times 2, which gives 20. So the area is 20. And then we need the, there's a well-known formula for the area of a parallelogram. It's base times the perpendicular height. Well, the perpendicular height is h, and that's what we're looking for. And so this perpendicular height is the area of the parallelogram divided by the length of the base. And the length of the base we can find using Pythagoras' theorem. So in effect, we Pythagorize 3 minus 2. And hence the area is 20 over root 13. Well, now let's have a look at the case where the line is not through the, doesn't go through the origin. But first of all, we'll notice that the regular formula for the distance of a point to a line is ax0 plus by0 plus c divided by the square root of a squared plus b squared, where a and b are the coefficients of x and y in the equation, c is the independent term in the equation, and x0, y0 are the coordinates of the point. And we're going to try and establish that formula. So here we have the case where, just generalized the previous problem really, so that the equation of the line is ax plus by is 0, and the coordinates of the point, instead of 4,4, we've generalized that to x0, y0. And so using the formula, we can see that the area of the parallelogram is ax0 plus by0, and that the base is the square root of a squared plus b squared. And hence the height, h, is ax0 plus by0, that's the area, divided by the base, root a squared plus b squared. Well, the Wikipedia website gives a proof of the general formula. It's really quite complicated, so I propose is easier. So here we've got now a general line, ax plus by plus c equals 0, and a general point x0, y0. And we're looking for the distance h. You can see on the right that the parallelogram has been formed by, first of all, sliding. What we're going to do is slide this line downwards to meet so that it passes through the origin. And to do that, we need the y-intercept, the value of the y-intercept, and then we're going to subtract from the y-coordinate of the point, y0, that distance, and also adjust the equation of the line. So at x is 0, for the line, when x is 0, y is equal to minus b over c. So that is the y-intercept. The height of that line above the origin at that point is minus b minus c. So we're going to subtract that from the y-coordinate of the general point. So we're going to move the diagram down, and y0, take away minus b over c, gives y0 plus c over b. The line, because it's been moved downwards, has a new equation, which is ax plus by is 0. We're now in a position to choose our general point, again, b minus a, to form the parallelogram. And we can then apply the formula to find the area of this parallelogram and divide by the base. And from that, we immediately get ax0 plus by0 plus c over square root of a squared plus b squared. So I think that's a very nice proof of the formula. And that's it for this workshop. I hope that has been of interest to you. Thank you.